So, if you've ever dug into geology, you've probably come across two different sets of names for the Earth's layers. You hear about the crust and the mantle, but then you also hear about the lithosphere and the asthenosphere. And it can kind of feel like they're talking about two completely different planets, but they're not. And figuring out why is actually the key to understanding, well, pretty much everything about how our world works.
So that's the big question, right? What is the deal with these names? Are they just different words for the same thing, or are they totally separate concepts? The answer is actually way more interesting than you think, and we're about to clear it all up.
All right, so here's the big secret. It's not one system versus the other. It's actually two different ways of looking at the exact same planet. The first set of terms, crust, mantle, core, that's all about chemistry, what the Earth is physically made of. The other set, lithosphere and asthenosphere, that's all about physics. It's about how those materials behave under all that incredible heat and pressure.
The easiest way to think about this is with a cake. You could describe a layer cake by its ingredients, right? You've got flour, sugar, frosting, that's its chemistry. Or you could describe that same cake by its texture. It has a hard, crunchy frosting, a soft, spongy middle, and maybe a gooey filling. That's its physics. See? Two totally correct ways to describe the exact same cake.
Okay, so first, let's look at the Earth's ingredients list. Its chemical layers. This is probably the model you learned first in school. It's the classic way of breaking down the planet by what it's made of.
Right on the outside, we have the crust. This is the thin, brittle, rocky shell that we all live on. From a chemical point of view, it's made of lighter silicate rocks, the stuff that kind of floated to the top when the Earth was a molten ball.
Go a little deeper, and you hit the mantle. And wow, this layer is huge! It makes up more than 80% of the entire planet's volume. Chemically, it's also made of silicate rock, but it's much denser, packed with heavier stuff like iron and magnesium.
And then, way down at the center, you get to the core. Its chemical recipe is pretty simple. It's almost all metal, mostly iron and a little bit of nickel. This is the super dense metallic heart of our planet.
So, simple enough, right? When you hear crust, mantle, and core, just think ingredients. You're looking at the Earth like a chemist would, breaking it down into its basic chemical parts. Okay, so we've got our ingredients down. Now let's talk texture. It's time to switch hats and look at the Earth like a physicist would, not based on what it's made of, but on how it acts.
So first, there's the lithosphere. Lithos is just Greek for rock, and this layer is exactly that. It's the strong, solid, and rigid outer shell of the Earth. Now this part is super important. The lithosphere is the tectonic plate. Whenever you hear about plate tectonics, you're hearing about these massive, broken pieces of lithosphere.
And what's just below that hard, rigid plate? The asthenosphere. Asthenos is Greek for weak, and this layer, even though it's still solid rock, is so incredibly hot that it starts to behave like plastic. It can slowly flow and deform over millions of years, kind of like super thick honey or putty. And that's the whole magic trick, really. This weak, squishy, flowing layer is what allows those giant, rigid tectonic plates to actually move around. It's the perfect natural lubricant that lets the continents drift across the face of the Earth.
So you see the pattern? When you hear lithosphere and asthenosphere, just think, how does it behave? You're classifying the layers based on whether they're strong and rigid or weak and bendy.
All right, we've got our chemical ingredients, and we've got our physical textures. So now for the aha moment, how do these two systems actually fit together? This is where it all clicks.
Take a look at this. This is where it all comes together. On one side, you've got the chemical layers we talked about. On the other, the physical layers. And you can see they aren't two separate things at all. They're just two different sets of labels for the same parts of our planet.
Now, this is the really cool part. Look at the rigid lithosphere on the physical side. Now trace your finger across to the chemical side. What do you see? It's made up of two different chemical layers. It includes all of the crust, plus that very top solid chunk of the mantle.
And that's it. That's the whole mystery solved. The lithosphere isn't a new ingredient, it's a physical property, a rigid texture. And that rigid zone is made up of two different ingredients, the crust and the upper mantle, that are stuck together and act as one solid plate.
Okay, so you might be thinking, great, but why does this even matter? Why do we need two different ways of talking about it? Well, it matters because understanding this one distinction is the key to pretty much all the geology we see on Earth.
Because that difference in physical behavior, having a strong, rigid shell sitting on top of a weak, flowing layer, that's the engine. It's what drives almost everything we experience on the surface, from the tallest mountains to the most powerful earthquakes.
It really breaks down into a simple three-step dance. Step 1, the rigid lithosphere is cracked into these massive plates. Step 2, the weak, slippery asthenosphere underneath gives them something to slide around on. And step 3, that slow, constant movement is what gives us earthquakes, volcanoes, and builds entire mountain ranges. Without this setup, our planet would be just a quiet, dead rock.
So in the end, these two systems aren't fighting each other. They're two sides of the same coin. One tells us what the Earth is made of, and the other tells us how it moves. And what this really shows us is that the solid ground we stand on isn't solid at all. It's a constantly moving, dynamic, restless system. And that kind of leaves you wondering, what will a map of our world even look like in another 100 million years?